When people first learn VLANs, everything feels stable. You make VLAN 10, you assign some ports, broadcast stay inside, done. And it feels like, cool, problem solved forever. But that stability is fragile, because the moment you connect a second switch, everything depends on one single thing. Can VLAN identity survive the trip between the switches? If the answer is no, VLANs collapse. Not slowly, instantly. Trunking exists because VLANs must scale beyond one device. And if you really understand trunking, you understand how enterprise networks stay structured, instead of dissolving into chaos. Before trunking makes sense, access ports must be crystal clear. An access port belongs to exactly one VLAN, and the end device connected to it sends normal Ethernet, untagged. So here's what's really happening. A frame enters the switch with no VLAN information inside it. The switch looks at the port and says, anything entering here belongs to VLAN 10. This is a huge idea. The frame didn't announce its VLAN. The host didn't label itself. The port decides. Access ports are simple because the endpoint doesn't need to know anything about VLANs. The switch does all the interpretation internally. Now scale it. Switch A has VLAN 10, VLAN 20, and switch B has VLAN 10 and also VLAN 20. You connect them with one cable. Now the design question hits hard. If VLAN 10 traffic and VLAN 20 traffic both cross the same link, how does switch B know which VLAN each frame belongs to? Because remember, the Ethernet frame doesn't naturally contain VLAN identity. So if nothing changes, VLAN meaning disappears the moment traffic leaves switch A. And if VLAN meaning disappears, the separation disappears. That's the problem trunking solves. Let's pretend we try to use an access port between switches. If the link is set to VLAN 10, then everything on that link is treated as VLAN 10. That means that VLAN 20 traffic can't cross. But if we set it to VLAN 20, that means that now VLAN 10 traffic can't cross. So access ports are exclusive. They can't multiplex VLANs, they can't carry multiple logical networks across one physical link. This is the exact moment trunking becomes necessary. Most people learn a trunk as a port that carries multiple VLANs. That is true, but it's shallow. The deeper truth is that a trunk changes where VLAN meaning comes from. Access port, VLAN is determined by where the frame enters. But trunk port, VLAN is determined by what the frame carries. That's an architectural shift. The port stops being the only source of VLAN identity. Instead, VLAN identity must travel with the frame. Let's reason this out. If multiple VLANs share one physical link and the receiving switch must keep them separated, then the frame must have a source MAC address, a destination MAC address, and also VLAN identity. Without VLAN identity, frames arrive stripped of context, switch B can't classify them, and separation fails. So the solution is simple conceptually. Add VLAN metadata while the frame is in transit. That metadata is called a tag. Now we introduce the name, but only conceptually. 802.1q. What it defines is simple at a high level. How a VLAN identifier is inserted into an Ethernet frame so that switches can interpret it. Think of the original Ethernet frame like an envelope. 802.1q adds a label that says this frame belongs to VLAN 20. And here's what does not change. The source MAC stays the same, the destination MAC stays the same, and the payload stays the same. We are not rewriting the message. We are adding context so switches can keep VLANs separated across a shared link. Now what happens inside the switch? A tag frame arrives at a trunk port. Step by step, the frame arrives, the switch checks, is it tagged? If yes, it reads the VLAN ID. Then it places the frame into the correct internal VLAN instance. And this part is subtle, but important. The tag does not tell the switch where to forward. The tag tells the switch which internal world to use. Because each VLAN has its own MAC table, its own broadcast domain, its own logical environment. So the VLAN tag is like, which universe does this frame belong in? Then normal switching happens inside that universe. This is extremely important. End devices don't understand VLAN tags. Your laptop expects normal Ethernet, so switches do this. When traffic enters from a PC, it's untagged. The switch assigns VLAN internally. When traffic crosses between switches, it gets tagged. When traffic exits toward a PC, the tag is removed again. Tags live in the middle, between VLAN-aware devices. To endpoints, VLANs are invisible. Now let's introduce the native VLAN. On a trunk, most VLAN traffic is tagged, but one VLAN is allowed to travel untagged. That VLAN is called a native VLAN. But why allow untagged traffic at all? Historically, it helped with compatibility and mixed environments, but conceptually, the key point is that a trunk still needs a default interpretation for frames that arrive without a tag. So the rule is, if a trunk receives an untagged frame, it assigns it to the native VLAN. That's it. That's the concept. Now watch how dangerous a mismatch can be. Switch A, native VLAN 10, and switch B, native VLAN 20. An untagged frame crosses the trunk. Switch A thinks this untagged frame belongs to VLAN 10, but switch B thinks that this untagged frame belongs to VLAN 20. Same frame, different interpretation. But what happens? Traffic leaks between VLANs unintentionally. Not because of hacking, not because of a bug, because default meaning wasn't consistent. This is why trunks must be conceptually consistent on both sides. Here's the mental model. A trunk is like one physical pipe carrying multiple separate streams. One cable, multiple VLAN lanes, side by side, and tagging is the mechanism that makes the streams separable again on the other side. Without tagging, those lanes blend into one mess. Trunking is basically multiplexing VLANs across one link. If trunking didn't exist, you'd have two choices. Number one, VLANs would be trapped on a single switch, or number two, you'd need one physical link per VLAN. And if you needed one physical link per VLAN, cable counts explode, design becomes unimaginable, and scaling becomes impossible. Trunking is what makes VLAN architecture viable. It's not optional, it's the mechanism that allows VLANs to scale at all. This is subtle, but critical. Even though a trunk carries multiple VLANs, it doesn't mix them. A trunk doesn't merge broadcast domains, it preserves them. It carries them side by side with boundaries still intact. So remember this, a trunk extends VLANs, but it doesn't combine them. Let's lock this in. An access port is one VLAN only, frames are untagged, and VLANs are assigned by port. A trunk port, multiple VLANs, frames are tagged, except the native, which take untagged, and VLAN is assigned by the tag. Access ports simply end devices. Trunk preserves separation between switches. Enterprise network design depends on this chain. VLANs create logical broadcast domains. Trunk preserves those domains across the topology. 802.1q tag carries VLAN identity between switches. Access ports hide complexity from end devices, and native VLAN provides default context for the untagged frames. If any piece of that chain breaks, the whole structure collapses. Trunking is the backbone that lets VLAN scale across switches, floors, and buildings. Okay, so final summary. A trunk is a switch port that carries multiple VLANs. Access ports cannot do this. VLAN tagging lets frames carry VLAN identity. 802.1q defines how that tagging works. Switches read tags to place frames into the correct VLAN instance. And devices never see tags. Native VLAN is the default mapping for untagged frames, and trunks extend VLANs across switches without ever mixing them. If you understand all this deeply, not memorized, but understood, the multi-switch VLAN design becomes very logical.